Welcome everyone. In this video I'm going to continue the previous video's experiments. So what I did in the previous video, I was using this heatsink and I was trying out different methods to cool it down. And what I did basically is I attached a thermometer here. Now it is attached here. So there was a K-type thermocouple clamped on this surface, and then I was running mist and air through the lamellas of this heatsink. And since the mist was evaporating from the surface of the lamellas, that was absorbing heat, and the absorbed heat removed the heat from this cooler, and therefore the temperature on this side was decreased. And this decrease was 4 or 5 degrees roughly. But what I did, it was not any kind of special cooling or something, so I was just using this heatsink, and there was no, let's say, load attached to it. So what you can see here is another CPU cooler. So in my previous experiment I was using this, but this has a slightly smaller area than the surface area of the Peltier cooler there. So this is like 35 times 35 millimeters. However, this cooler has an area of 40 by 40 millimeters. So it is perfectly overlapping with the area of the Peltier cooler, and that's very good for us. So I removed the fan from this gap, and I will just put this 8 centimeter fan right there. And what we will do is that I will apply some current on this TEC 708 unit, and we cool the hot side with the CPU cooler, and we measure the temperature of the more or less isolated cold side with a K-type thermocouple, which can be seen here when I turn on this thermometer. So we will see what will be the temperature after, let's say, 5 minutes of waiting, and we note that down, and I will apply the exact same current. So we have the same power available for the cooler, but I will add water vapor to the equation basically. So I will use my mist box from my previous experiment, and I will push the mist through the lamellas of this heatsink, and we will see if we can reach a lower temperature on the cold side by just adding some extra cooling on the hot side. So what we should do now is we should turn this on, and you can see that it is showing 26.7. This is pretty much the room temperature. So I just simply put this fan in the gap, and I just start it up. So you can see that the temperature will not really change, because yeah, I'm just pushing the room temperature air through the heatsink, so that should not change anything. So I have the power supply running. I will use this side, and I start it up. And of course now some current is running through the Peltier cooler, so you see a small decrease. So let's see if we can go by 3 or 4 amperes. Let's run this thing at around 4 amperes. So as you can see, 3.95, that's pretty much the same which is shown on this display, and 10 volts, I can also check that. So I will try to make it visible for you as well. So hopefully you can see something from the screen. $10.14. So now you can see, even at 3.8, 3.9 amps, with this 8 ampere unit, we have minus 20 degrees basically. As I said the word, it immediately changed to that. So minus 20 degrees. Let me put another thermometer here just to monitor the air coming out from this thing. It might be not the best idea to do it like that. So if I read the temperature from this, now this is the channel number 2, that's 28.5. And this is the channel number 4, this represents the room temperature, that's 26.2. So a little bit higher than the room temperature, but still quite close to it. So we don't have too much load on this. But you can see that with these details, so we are running this unit at roughly 40 watts. This power meter here is showing 38.3, and that's basically the reality. So we could see that the voltage and the current was the same as we could measure with the multimeter. So that's very nice. So with 40 watts of applied power, we could go down to minus 20.4 degrees within just a few minutes. And again, I have to emphasize that now the cold side of the Peltier cooler is insulated. It is separated from the environment. There is basically no heat flow from the cold side towards the hot side, which means that the QC, which is the cooling power of the Peltier cooler, is very close to zero. Therefore, the DT, so the temperature difference between the cold side and the hot side, can be quite high. And the same applies in the other way. So if you want to pump a lot of heat from the cold side to the hot side, the DT, so the temperature difference between the two sides, will be small. So now I'm reading 29.7 here, and I'm reading minus 20.5 there. So that is at least 50 degrees difference. So if you have 50 degrees DT, and I believe that the temperature here at the cold side is even higher than 29.7, so if you have this high DT, that also means that the QC, the heat transferred between the two sides, is very low. Therefore, you cannot cool with this efficiently. So in order to cool something, you have to sacrifice the temperature on the cold side. So you cannot go this low if you want to, let's say, continuously pump heat from one side to the other. So I think we waited enough, and now the temperature is more or less stable. If we wait, let's say, 10 more minutes, maybe we get 1 degree difference here, but it will not change significantly. So we can say that with these settings, this is the maximum that we can get, or this is the minimum that we can get. And now the temperature here went up to 30 degrees. If I touch the heatsink from both sides, let's say, I cannot really feel any difference from my hand or something. It's not warm, so it's quite okay to touch it. So let's say that this is our value at air, at dry or relatively dry air. So the next step would be to set up my box, the water box, and repeat this experiment. So now I have to disassemble a few parts here and come back to you with the box. So here is the box. It's the same as from the previous experiment. So it's filled up with some water. The mist will be here in the rest of the box when I turn on the mist maker. So this fan here will push the air into the box, and then the mist will be pushed out through this hole here. So the mist has to go through these two layers of heat sinks. And then you can see that the temperature now is 28.4 on the cold side. And the reason for that is because I shut down the Peltier cooler, and then I haven't ran the fan for a long time. So therefore some heat went back towards the cold side just due to a simple heat conduction. So now it's a bit higher than the room temperature, but at least now we can see that it's not cooled down below the room temperature or something, so the initial temperature will be higher than the room temperature. That's okay. And once again, the room temperature is measured here, 26.2 degrees. And now I have a thermometer at this corner, which is slightly above the water level, but it's inside the box, so it will be surrounded by the mist when I turn on the mist maker, and that is showing 24.2 degrees. I put this thermometer here, it is touching the heatsink down there, it's 28.5 degrees, and this random guy here is just 26.7. So we are fine. The only thing to do is to first I generate some airflow, and we will see if the temperatures are changing. I expect a little bit of change maybe, because we start to move like moist air or humid air through the heatsink, but it should not be that significant if there is any change. So this is done. So the air should come out here, most of it at least. So now I have to attach the other side of the cables, and then I have to go to the previous values, which were 10 volt and 4 amps. But before doing that, I have to do some cable management. So this will be better now because I can move the cables in a better way, and hopefully you can see the screen more easily. So this is wired up, and I just have to increase the voltage because the current is set up to be 4 amps. So now we are just pushing the air through this, so we will see what happens. So 3.84, so I can increase just a little bit. So 3.97, this was the same as previously. So now, as you can see, the temperature stuck at minus 17.7 because we are not pushing the air through the fins in the same way as previously. So what I could try is just simply put the fan there and see what happens. So this should decrease the temperature here, and hopefully it will do that. So now you see the change. So this is a direct proof that you have to cool the hot side properly in order to reach the desired temperature on the cold side. So now you see we dropped 1 degree just because I moved the fan to the proper position. But now, as the airflow is a bit limited, because basically there is a hole here at the corner of this box on the lid, and that is the only way where the air could enter. It might be so that we don't reach the same temperature here, So as previously, that was like minus 20.5 degrees without any vapor introduced to the system. So now it seems that the temperature or the decrease of the temperature started to slow down, and we are more or less at minus 19.5, 19.6, but it started to slow down. So let me start this experiment now by turning on the mist maker, because now you see that the change is quite slow. So if we have the mist, we should have some significant change here. So let's see what happens. So you can see that the water started to move because I started to generate mist, and you can see how quickly the temperature started to drop here. So it's basically 1/10 of the degree Celsius at every second. So now we passed our previous value, which was minus 20.5, minus 22. So again, you can see that the better you cool the hot side of the Peltier cooler, the lower the temperature will be at the cold side. So now you see we are at minus 24. If we wait a little bit, I think we can also see minus 25. I'm just hoping that the mist which is generated here is not being condensated on the electronics inside the power supply. So that would be very bad. So once again, the fan is running in between these two lamella or series of lamellas. The cold side doesn't have any heat transferred because it's insulated, so the cold side is in a very weak contact with the environment. We are measuring it with a K-type thermocouple, minus 24.6. The power running to the Peltier cooler is same as previously, so roughly 40 watts. The temperature difference between the two sides still 50 degrees Celsius. So the cold side is, as you can see there, minus 24.7, and the hot side, well, I cannot precisely tell, but based on this thermometer here, is 25.7. So it's roughly room temperature. So we keep it very close to the room temperature. And actually we are not cooling the two sides equally, so it might be that I can improve this cooling a bit more. Let's wait until this goes below 25 or reaches 25, and then I put the fan on the hole here, which should be a bit better, because now the fan more or less restricts the moisture to a smaller diameter here, so the moisture is not in contact with all the parts of the heatsink. So let's try it now. Okay, so it seems like this was a bad idea, because then the temperature started to increase. And I think this is also a bad idea because we are not too close to generate enough pressure drop. But this method seems reasonable. So as you can see, if you can master the geometry of this system, so you can optimize the size of the heatsink and also the size of the fan, also the distance between the heatsink and the fan, the amount of mist being generated, you can have quite significant temperature differences between the two different kinds of setup. Let's call this wet cooling, and the previous cooling was the dry cooling, and now it's like 4 degrees difference between that, but that's very nice. So you gained 4 degrees just by introducing a few extra parts, like a mist maker, a container with some water, and that's all basically. And yeah, so once again, what happens here is that the mist, which is very fine droplets of water, is being sucked in between these lamellas, and then they touch the lamellas, and then they evaporate from the lamella of the heatsink, and the evaporation absorbs heat, and then it removes heat from the heatsink. And as you can see, that results in a better cooling of the hot side. Therefore, the cold side will go to lower temperatures. And as you can see, in this certain setup, this improvement was 4.5 degrees almost. So we are stuck at 24.9, minus 24.9, and this is just a single Peltier cooler. And just for fun, I increase the current and see what happens. So let's go to 5 amps. Okay, so this is surprising. I was not expecting this nice improvement. I have never reached this low temperature with just a simple stage of Peltier cooler. So I just hold. So 5.9 amps, and I try to measure the voltage as well. .26. So these are correct numbers here. It's like 0.1 difference in both values. So that's very nice. Okay, let's go to 5.5. And actually this is the maximum that I can extract from this power supply, because this power supply is running only at 13.5 volts, because it's a roughly 12 volt power supply. So 13.5 volts, 5.5 amps, that's like 73 watts, and we reached minus 27.6 degrees Celsius. So with this, I think we can go even more down with a better power supply, and maybe with a somewhat better airflow. And maybe we can go below minus 30 just with a single stage of Peltier cooler. So now I shut this down because there are too much moisture in this area. So let's just get rid of this and remove this. So as you could see, we could reach very, very low temperatures with a single stage of Peltier cooler. Once again, this is a TEC 12708, so it's an 8 ampere unit. We were able to run it without any kind of performance issues at 5.5 amperes. And you could see that we reached minus 27.4 degrees Celsius, which is amazing, I would say. So this experiment again shows that you can use vapor made by a simple mist maker and use the advantage of evaporation of water and cool your Peltier cooler more. So as you could see, that we were able to reach 4 degrees difference with the same given performance, so 40 watts on the Peltier cooler, and that is not the cooling power, that is the 40 watts given to the Peltier cooler with the power supply. And at 40 watts of power, without vapor we reached minus 20.5, and with vapor we were able to go minus 24.5 roughly, and that's a very nice difference, I would say. So with this experiment we could show how to improve this and how to get some better numbers. So in some future videos I will try to further improve this system to make it more clear, have some better airflow, to not expose these fans to the water, because these are regular fans and I'm not supposed to run them in this kind of environment, so it's wet and everything. This is not made for this. So I hope that this video was useful, and I hope that I showed something interesting. I think this experiment is very good because it's so simple. You don't have to add too much things, but you can see some significant improvement in your cooling performance. So it is very simple and very useful. So don't forget to subscribe if you haven't already subscribed to my channel. You can visit my website, curiousscientist.tech, and see you in the next video.